Alright, getting ready to analyze the inorganic compounds in this organic sample. Here we go. I think I'm going to oxidize some of these bonds with perchloric acid.
Whoa, 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 Nick, what are you doing?
I'm getting ready to oxidize the bonds and break down the organic sample so I can analyze the inorganic sample.
No, you're not. Do you realize what you're using?
Yeah, perchloric acid. It's a great oxidizer.
Nick, it's extremely toxic and highly explosive. You're not even using a hood.
Why do I need one?
Nick, you know better. Dr. Samai taught you better than that. And you didn't even start by oxidizing with HNO3.
Well, yeah, I thought about it, but didn't really find it necessary.
Nick, you obviously don't know proper wet ashing procedure.
Well, do you want to tell me about it, Alan?
Yes, I do. Put that stuff down before you kill someone.
Alright.
Chalk that up to another life save. So today I'm going to talk to you a little bit about wet ashing procedure. What Nick was doing was he's trying to expose inorganic ions to a solution in order to be analyzed. He's taking those inorganic metals or ions from an organic sample. He has to break down that organic sample in order for him to be able to run analytical procedures on the metal that he has in solution. Like I said, this is called wet ashing. I'm going to tell you a little bit about it. First things first, let me define what wet ashing actually is. Wet ashing is the destruction of organic material in a sample by a liquid reagent prior to the analysis of an inorganic component. So we use wet ashing for preparation of samples for analysis of specific minerals. These minerals ultimately end up in an aqueous solution, and we can therefore run analytical tests to figure out how much we have and what actually is in our solution, what metals are contained in that sample. We did this in lab when we talked about the metal concentration in specific vitamins. So we could ultimately use wet ashing for things like determining the amounts of metals in food samples, or even how many metals are in a superhero vitamin. We didn't realize it at the time, but what we were doing was wet ashing. So ultimately, just kind of an overview of wet ashing. We're going to take some type of highly oxidative acid, like HNO3 or perchloric acid. We're going to heat them up, put our sample in there, and let them oxidize all of the organic compounds that are surrounding our inorganic materials. There are some advantages to wet ashing in using this procedure, and that's that there is little loss of our volatile minerals that are within the compound. It's more rapid than dry ashing. So you would think, because of wet ashing, dry ashing has to take some type of form. And what dry ashing does is we actually take the component in a non-liquid setting, and we just vaporize it. We heat it up in the presence of oxygen, and we're able to extract our minerals. But that's for a different discussion. We're not going to talk about dry ashing, only wet ashing today. The disadvantages to wet ashing is that it's very labor intensive, and you have to take lots and lots of precautions. Nick just about blew Gallahue Hall up because he didn't operate underneath a hood. When you're working with perchloric acid and nitric acid, always, always work under a hood and make sure you use precautions such as safety glasses and gloves. 2 gloves, if you're comfortable. Like I said, these compounds are highly dangerous. Just an example of how dangerous perchloric acid actually is. In 1947, 17 people were killed when a bath consisting of only 1,000 liters of perchloric acid exploded. In this explosion, the plant that housed the bath, along with 14 people, 40 automobiles, and 25 other businesses, all exploded. This happened with only 1,000 liters of perchloric acid. So it's highly dangerous stuff. So now let's go to the problem that was actually in the problem set. Number 9 read, an organic soil sample underwent a wet ashing procedure using 2 aliquots of concentrated HNO3, followed by 1 aliquot of concentrated HClO4, to prepare the sample for arsenic analysis by atomic absorption spectroscopy. Why was the perchloric acid added after the 2 aliquots of HNO3, and why was HCl not used in this procedure. For the solution, HNO3 is used first in order to oxidize the weak bonds. HNO3 is essentially the first assault against the organic molecules that are present within our component. We have to break down these bonds first before we add our perchloric acid. So in actuality, we're going to use a couple rounds of HNO3 to make sure our sample is pretty much oxidized before we completely clean it up with the HClO4. Like I said, HClO4 is then put in last to clean up the solution, to ultimately break down the remainder of the bonds that need to be oxidized. This allows us to extract our inorganic component. Now remember, we're doing all of these procedures with heat. So we're heating up this liquid in order for this reaction to actually take place. Heat's, like I mentioned before, maybe up to like 325 degrees Celsius. That's just a ballpark. So after we've added our HNO3 and we've added our HClO4, we've broken down our organic compounds. Now it's important to add the HClO4 last. The reaction of HClO4 with our organic compounds is so thermodynamically favored that if we keep too many bonds prior to adding our HClO4, an oxidation occurs that's so great that we could have an explosion. So it's pretty dangerous to just add straight HClO4 prior to first oxidizing with HNO3. So in this example, we didn't use HCl because when mixed with arsenic, we create highly volatile chlorides. These chlorides get lost in the solution and are ultimately very toxic. So for our own safety, we chose to not use HCl as one of our oxidizing acids. So just to review, a given generic reaction of wet ashing would include something like this. You would first heat the sample slowly and boil it with HNO3. We're going to boil the solution all the way down until the HNO3 almost evaporates, so our sample is nearly dry. We're then going to add some more HNO3 and repeat that procedure, maybe 2, 3, or even 4 more times. We want to make sure that our solution is about as oxidized as it can be. We're then going to add our perchloric acid in at the very end to basically clean up our solution. We're going to make sure that every single bond now is oxidized, and we've eliminated all of our organic material. Again, it's important to add the HClO4 last. This could save your life in a chemistry lab. So that's it for wet ashing. Like I mentioned over and over again, wet ashing is an important procedure for allowing us to analyze inorganic materials. But you have to do it with caution. Always think safety in the lab. To illustrate this, I'd just like to ask, what do you do with a dead chemist? Nick, any idea? What are we doing with a dead chemist?
Gee, I don't know, Alan. What would you do with a dead chemist?
Well, if you don't take precautions with perchloric acid, if you're a dead chemist, we're going to bury them. That's all for our lesson today on wet ashing. Thanks.